All right, 14b, still talking about log functions, context, and data modeling. So it says, we've been able to fit linear and quadratic models as well as exponential models from data. Let's continue to use technology to explore some real-life relationships between two variables that behave in a logarithmic pattern. So example 8 says, determine the equation of the log regression function for the data. So regression, that's using that stat edit. So we're going to go into our stat edit. And we're going to put our data in. So put your x's in L1 and your y's in L2. A says determine the equation of the logarithmic regression function. All right, so then we're going to go to stat, go over to calc. All right, and when you do that, you can go through your list. You see, starting at 4, you got linear regression, 5 is quadratic, 6 is cubic, 7 is quartic, 8 is linear again, 9 is a natural log, 0 is exponential, A is power, B is logistic, which is not the same as a log, okay? C is sine, D is, and then it starts getting weird, and then it starts over, okay? So the only thing we have there is number 9, which is a natural log. Now it says determine the equation of the logarithmic regression. It didn't say what base, so we're going to use the natural log. So let's choose number 9, which is the ln. It tells you to, your x list was in L1, your y list is in L2. And if you want to store the regression equation, remember, you can go to alpha trace and plug it into y1, and then go down to calculate. And so what you'll see there is, all right, so what you see there is it tells you that y is equal to a plus b, natural log of x. Tells you what a and b are. And if you remember to turn on your diagnostics by going to mode and putting diagnostics on. If not, you might want to do that. I forgot to remind you. So it'll give you your r squared and your r value, okay? All right, so on this one, we see that our equation is going to be y equals, our a is negative 2.646 plus B, which is 0.952. Whoops. Sorry, wrong number. Our B, which is 4.654. And then it's the natural log of x. All right. B says use the function to predict f of x when x is 10, rounded to the nearest tenth. So remember, this is our y. This is the same thing as f of x. So we're just looking for f of 10. So we're just going to plug 10 into our function. And we can see that it is 8.0704. Or if you save this in your y1, if you stored the regression equation there, then all you have to do is go to your table, go to where x is 10. And so it says round to the nearest tenth, so we know that that's going to be 8.1. And then it says, what is the residual for the data value of 4, 4.5? All right, so remember the residual. We talked about this a while back. So your residual is your y minus your predicted y. So in this case, the y value of 4 is 4.5 minus the predicted value. Well, I need to go to my equation then, because that's what we found here was actually the predicted y. So I'm going to go find f of 4. And let's see if I check that. It is going to be 3.8058. And so that's what I'm going to subtract here. So 3.8058, which is 0.6942. So that would be our residual for that point. Remember, residual is your actual minus your predicted. Predicted is your line because it's based on a prediction. All right. Example 9 says the table below represents the speed of some type of fore, which is a rowing boat used in the sport of competitive rowing. So we have our time and we have our speed. So let's put our time in L1 and our speed in L2. So when I go into my stat edit, if I want to clear the data that's up in there, I can go on to the L1, hit clear and the down button. And then go up to L2, hit clear and the down button. Or I could clear my entire calculator. Or I can just try to rewrite over the ones and then go through and delete the ones I don't need. Alright, so I'm going to input my data here. Alright, A says determine the equation of the log regression function. So stat, calc, linear regression. I'm sorry, not linear, natural log regression. My x's are in L1, my y's are in L2. I'm going to store this regression equation. Uh-oh, I hit the wrong button. Give me just a second. So I'm going to store it. So alpha trace in my y1 in case I need it and calculate. So I can see that my equation is y equals 1.541 plus 2.558 natural log of x. Now, I don't know if I'm going to need it yet or not, but I'm going to come over here and I know that the r value is 0.9909. I'm going to write that down because I see in B it wants me to find a linear regression. And I don't want to have to rerun this if I need that r value. So right now the r is just extra information on that one, but I'm writing it in case I need it. All right, find the linear regression model for this data. So stat calc 4. I'm going to save that in I'm going to store it. So alpha trace, I'm going to put that in y2 and calculate. And so I get y equals 0.789x plus 1.5. And it had an r value of 0.964. Determine which model fits the data better and why. So the log function, the log model has a higher r value, so the regression is, so it's a better fit. So the log model is r equals 0.9909. And then it says use the best model to find when f of x equals 8 and explain the meaning and context. All right, so when f of x equals 8, so I'm going to go through in my y1, I had the log equation, okay? So in y1 is my natural log function. And in y2, I'm going to type in 8, and I'm going to just find where they intersect. All right, so in y2, we had that linear function, but we don't need it, so I'm going to clear it out and put in an 8. And I'm going to go to graph. And I don't quite see it, so I need to extend my window. And so I know I need to go to the right, so that's my x max. So I'm going to take it out a little bit, take it out to 20. And now I can see it, so I'm going to find the intersection. So second trace intersect. And I find that the x value there is 12.484. So at 12.484, remember that's your x, and your x is your time. So at 12.484 minutes, the boat will reach a speed of 8 meters per second. All right, example 10. says a university study on sleep related to caffeinated drinks is shown in the table below. Participants were given 250 milligrams of caffeine in his or her bloodstream. The caffeine levels was measured at various times. Determine the equation for a log regression function for the data representing time as a function of caffeine level. All right, so time is a function of caffeine level. So that means that my caffeine level is my L1 and my time is my L2. So go ahead and type those in your calculator. Run your logarithmic regression. And so we should get that y is equal to negative 40.801 minus 7.214 natural log of x. And then I'm going to go ahead and write down that r value just in case I need it for anything, so I don't forget it. Then B says, find the time it takes for an average person to metabolize 50% of the caffeine in their bloodstream. Round your answer to the nearest tenth of an hour. So if we start out with 250, 50% of that is 125. So I'm looking for my function at 125. So I saved my equation in my y1. And so to help me, I just took, and I remember we talked about how to jump around in your table. So I went to second window and I did table start at 125. And when I did that, I can see that that's equal to 5.9698. All right. And so to the nearest tenth would be 6.0. So it takes approximately 6 hours to metabolize 50% of the caffeine. All right, C says Avery drank an energy drink containing 250 milligrams at 9 a.m. How much caffeine will be in his bloodstream 10 hours later? Round your answer to the nearest milligram. Well, 10 hours, that time is the y value, so we're looking for the x. So I'm going to do the same thing I did earlier. So I got my equation of y1. I'm going to put 10 in y2, and I'm going to go find their intersection. I am going to have to extend my window a little bit out. So, and then I'm going to find the intersection. So I find it's at 71.497. Right, so that means that Avery, so how much caffeine will be in his bloodstream 10 hours later? So Avery will have about, so to the nearest milligrams, so 71, exactly, so 71 milligrams. Have about 71 milligrams of caffeine in his bloodstream. Ten hours later. All right, D says a study found the majority of participants were able to sleep when their caffeine levels fell below 70 milligrams. Find the time to the nearest hour for the body to metabolize the caffeine to reach 70 milligrams in the bloodstream. So the 70 was the L1s, the milligrams, so the caffeine, so that is my X value. So I'm looking for F of 70, which is 10.153. So to the nearest hour, so we're looking at 10 hours. So it takes about 10 hours to metabolize the caffeine to reach 70 milligrams. And E says, using the regression equation, find the x-intercept, explain the meaning of the x-intercept in context to the sleep study. So remember, your x-intercept is when your y value is 0. So I'm going to go put where y2 is equal to 0. I'm going to extend my graph a little bit more, but I'm going to find that x-intercept, when I find its intersection, is at 285.963 milligrams. All right, so the x-intercept is 285.963 milligrams. This represents the amount of caffeine at time t equals 0. Based on the regression model. All right, example 11 says the wind speed S in miles per hour near the center of a tornado is related to the distance d in miles that the tornado travels by the equation S of d equals 93 log of d plus 65. A tornado whose wind speed was 220 miles per hour struck town in Nebraska. How far did the tornado travel? All right, so they gave us an equation here. And let's see, how far did the tornado travel? So we're solving for D. So I need to know S. Well, S is my wind speed, and it told me that the wind speed was 220 miles per hour. So I'm going to plug that in, and I'm going to solve this for D. All right, so subtract the 65. Divide by the 93. You can reduce that if you want to, but you don't have to because we're going to use our calculator in the end anyways. So I'll end up with 155 over 93 is equal to log of D. Since we have log equals a number, we can just change it to our exponential form. So 10 to the 155 over 93 equals D. And so D is equal to 46.416 minutes. No, not minutes, miles. Sorry. Wrong button. So we know the tornado traveled 46.416 miles. All right, and then example 12 says Mr. Craig gave his students a poster of math properties. They studied the image for 90 seconds. Beginning one day later, a quiz was given each day to test their memory of the poster. The table below represents an average score for each day. Use logarithmic regression to model the data. So I'm going to go put this in my stat edit again, run my log regression. And so we get y is equal to 76.070 plus a negative, so minus 7.882 natural log of x. It says then use your model to predict the average test score after 14 days. So the days is my x's, so the f of 14. So I'm just going to, I saved my regression equation in my y1. So I'm going to go to my table, look at 14, and it tells me it's 55.27. So the average test score after 14 days is approximately a 55. All right, and that is the end of 2.14.